Hi, welcome back to the series on binary operation. Today we'll be looking at the closure property, which is the first property underneath binary operation. In the next video, we'll be looking at the commutative property. So do well to stay tuned and also share to your friends so they can learn also. Now, for closure property, we are told that a set is said to be closed under a given binary operation delta if for any two elements from the given set itself, the result from the binary operation is a member of the set. So what this is simply trying to tell us is, so let's say we have set R being a set of all real numbers from negative infinity to positive infinity. So let's say I have R being the name of the set from negative infinity. So let me just use that. I'll represent that with my dot, dot, dot. So I'm coming from negative infinity, minus 3, minus 2, minus 1, 1. Okay, so this should be 0, 1, 2, and 3. So again, dot, dot, dot. So moving from negative infinity to positive infinity. So what we're now saying is, by the time we combine any two numbers, so let's pick any two numbers. So let's pick minus 2, and then let's pick 4. So of course, minus 2 and 4, that's the element of these real numbers because this guy is moving from negative infinity. So that's your minus 1 million, minus 1 billion, minus 1 trillion. So up until positive infinity. So minus 2 is a member of this set. Positive 4 is a member of this set. So minus 2, 4, they're all elements of R. Now after combining these two guys, if the result you're having can still be found inside of this set, then definitely we can say that the set R is closed under such operation. So let's try and combine this using addition. So let's say we're saying minus 2 plus 4. Now the result minus 2 plus 4 simply gives me 2. You can see that 2 also is an element of this real number. So we can say that the set R is closed under the operation addition. So set R is closed, set R is closed under the operation addition. Alright, so you can see quite easy. So when you combine two elements of particular set, if the what's it called? If the third element or the result rather can be found inside that same set, then definitely we can say that the set is closed under such operation. Now you see that it doesn't really matter the number we pick. So let's say we pick minus infinity and then we pick positive infinity. Now the number will still be found inside of the set. So that's why we are coming to this conclusion that set R is closed under the operation addition. So it has to be true for all the members. Okay, so let's try and combine again under subtraction this time around. So let's say minus 2 minus 4. Okay, so minus 2 minus 4 or minus 2 minus plus 4. So since we're taking a positive 4, so minus plus 4. So this becomes minus 2 minus 4, and then this becomes minus 6. Again, minus 6 is an element of this set R. So again, what's the conclusion we can come to? So it doesn't matter which number we pick again for subtraction. So when you subtract any two real numbers, the result will always be another real number. So we can say that the set R is closed under the operation subtraction. So set R is closed under the operation subtraction. So let's see whether the same thing is true for multiplication. So for multiplication, let's try and clear this. So clear this and then so still stick to the numbers we picked earlier. So we picked minus 2 and then we want to multiply it with positive 4. So minus 2 times positive 4. So this gives us negative 8. Again, negative 8 is also a real number. Yeah, a real number. So definitely we can say that the set R is closed under the operation multiplication. Now remember, no matter the number you pick here, no matter the number you pick, so whether I take minus 3 and positive 3, I will still have a real number. Whether I pick minus 3 and 0, I will still have a real number. So of course, due to time, and then I don't want this video to be lengthy, so I'm only showing one example, and then we're coming to our conclusion. All right, so what about division? So what about division? For division, the set R won't be closed because there are some values. There are some values that R won't have an answer. R won't have an answer. So let's say, for instance, so this time around we'll be changing our value. So let's say we have two members, 4, 0. And we're told that 4, 0 is an element of this real number. And by the time we do 4 divided by 0, so we're trying to combine these two guys together. 4 divided by 0. The operator here is division. So 4 divided by 0 doesn't return a real number. So rather, we say this is infinity, or not infinity, undefined rather. Sorry about that. Undefined or indeterminate. So undefined. So 4 divided by 0, undefined. So you can see that the result we're having here is undefined. So undefined is not a real number. So definitely this set R can't be closed under the operation division. So for set R to be closed, it means any real number you combine together. Of course, if I do 4 divided by 2 or minus 2 divided by 4, I'll have an answer which is a real number. But if there's a number that you divide and then you're not going to be having any other answer, then definitely we can see that the set R is not closed. Of course, we've talked about this property underneath function. So we have a video on that. You can do well to watch functions, that is values where you wouldn't have any answer or any valid answer. Okay, so let's look at more examples, a much more refined example. So let's try and write that on the screen. So we are told that a binary operation delta is defined on the set T equal to 1, 2, 3 as A delta B equal to 2A minus B. Is the set T closed under the operation delta? All right, so when we are given this, since the elements we are given here, 1, 2, 3, the cardinality is 3. So the best thing to do is to draw a table that showcases the row and column. But this is not the only way to do it. You can just try and combine the 3 elements or the 3 members underneath this operation. So combine the 3 numbers underneath this operation, and then you see whether the resulting number will be a member you are given here. So what do I mean? Let's do a table. Table is always the easiest. So the operation I'm dealing with is delta, and then the numbers I'm having, I have 1, I have 2, I have 3. So write it. So let me write this properly. So let me write this in the column section, and then so 1, 2, and then 3. So this way is easier because this means 1 delta 1, 1 delta 2, 1 delta 3, 2 delta 1, 2 delta 2, 2 delta 3, 3 delta 1, 3 delta 2, and then 3 delta 3. All right, so without wasting much time, so let's try and fill in the gap. Remember, so we start with the first one, 1 delta 1. So pick the ones from the, from the row, and then the one from the column section. So combine them underneath this row. So what do we have here? We are told that 2 in 1, okay, minus 1. Remember, A is 1, but this first 2, A is 1, B is also 1. So 2 times 1, that's 2, minus 1. So this is 1. So I write my 1 here. Okay. Now 1 delta 2. So what is that going to give me? So 1 delta 2. Do the same thing. So my A is 1 minus my B is 2. So 2 times 1, that's 2. 2 minus 2, so this is 0. And then I write 0 here. So immediately I flash back to my set, the original set. Remember, we said for a property or for a binary operation to be closed, it means after combining 2 elements from that set, the results you are having should also be found in that set. So I can't find 0 here, and then I'm having 0 here. So automatically, that should tell me that this set T is not closed underneath this operation delta. But let's just try and finish the table so we see how this works. So 1 delta 3, so instead of using the writing on the screen, I'm just going to be multiplying directly. So we have 2 times 1, which is 2, minus 3. So this gives us minus 1 rather. So not minus 3, minus 1. And this plus this other one. So 2 times 2, that's 4, minus 1. So that's 3. So this gives me 3. I can find 3 in this set. Yeah, but of course, this set T is not closed underneath this operation. Okay, so 2 delta 2. So 2 times 2, that's 4. 4 minus 2. Again, this is 2. And then lastly, 2 delta 3. 2 times 2, that's 4. 4 minus 3. So this is 1. Okay, so 3 delta 1 now. So 2 times 3, 6. 6 minus 1. So that is 5. 3 times 2, 6. 6 minus 2. So this is 4. And then 3 times 2, which is still 6. 6 minus 3. So this is 3. So you can see that this is an odd one out, another odd one out, another odd one out, another odd one out. So if at all, even if it is one that is odd that you can't find in this set, then definitely this operator is not defined underneath this or this set rather is not defined underneath this property. Okay, so let's look at one more example before we call it a day in closure property. Okay, so for the last example, we're told that if set S equal to 0, 2, 4, that is the members of set S are given as 0, 2, and 4, and x o dot y has been defined to us as x plus y minus 1 over 2xy or minus 0.5xy as what is written on the screen. We're now asked to find or determine if the set S is closed under O dot. So just like the way we did the previous what's it called, example. So why are we using table? Because we have 3 members. I think it was just 2. So we just group these 2 together, the 2 numbers, and see whether the result is either of the 2 numbers. But if you have more than 2, then it's always better to use a table. So using our table, draw the same table or the same type of table we drew the last time. So what's the operator? O dots, and then I have 0, I have 2, and then I have 4. So write it in the column aspect. So 0, 2, and also 4. So let's try and combine these together using this rule that's been defined for us. So 0 O dot 0. So we have 0 plus 0 minus 0.5 0 times 0. So you can see that 0 times 0, 0 times 0.5, 0. 0 plus 0 minus 0, everything will still be 0. All right, so for the next one's 0 dot 2 or 0 O dot 2. So we have 0 plus 2 minus 0.5 in the bracket of 0 times 2. Okay, so 0 times 2, that's 0. 0 times 0.5 again, that's 0. 0 plus 2, so we have 2. Okay, so again, this one, of course, this will also be 4, isn't it? Because we have 0 plus 4. So everything here, since we have 0 here, so everything times 0 becomes 0, and everything here becomes 0. So 0 to 4. All right, so let's try with this. Again, this also 2, 0. So again, if we start, so 2 plus 0 minus, again, everything here also becomes 0 because 2 times 0. So let me just put 2 here. Now for the next one, 2 plus 2, okay, minus 0.5, 2 times 2. Okay, so 2 times 2, that's 4. 4 times 0.5, that should be 2. So 2 plus 2 is 4, and 4 minus 2 should be 2. Okay, next one, so 2 plus 4, okay, minus 0.5 and 2 times 4. Okay, so 2 times 4 is 8, 8 times 0.5, that should be 4. Then 2 plus 4 is 6, 6 minus 4, again, we're having 2. Okay, I hope this makes sense. 4 and 0, so again, this will be 4 because there's a 0 there, and then this other part will be 0. Okay, so how about 4 and 2? So for 4 and 2, would have 4 plus 2 minus 0.5, 4 times 2. 4 times 2 is 8. 8 multiplied by 0.5, that's 4. 6 minus 4, that's 2. So this is 2. And lastly, 4 and 4. So 4 plus 4, 4 times 4 is 16. 16 times 0.5, that's 8. 4 plus 4, 8. 8 minus 8, that gives us 0. So you can see that all the answers we're having from this point to this point, they are all elements of set X itself. So that is the results are all elements of this set. So definitely, you can now come to a valid conclusion and say that the set X is actually closed under the operator O dot. All right, so with this, we've come to the end of this lesson on closure property under this binary operation. So if this video has been helpful, do well to share to your friends, like, subscribe. And if there's any other challenge you might be having under this closure property, you can do well to put it in the description box. Don't forget, in the next video, we'll be treating the commutative property. Thank you for watching. Stay blessed and bye-bye.